What is radiative exchange in mechanical engineering? Imagine standing near a campfire on a chilly night. You feel the warmth not just from the air around you but from the fire itself. That's a simple way to think about radiative exchange. It's how heat moves through electromagnetic waves, mainly in the infrared spectrum, without needing air, water, or any other medium. In mechanical engineering, understanding this process helps us design better systems for heating, cooling, and insulation. Radiative exchange happens when surfaces at different temperatures emit and absorb thermal radiation. Every surface above absolute zero emits energy, and the amount depends on its temperature raised to the fourth power. This is described by the Stefan-Boltzmann law. The hotter a surface, the more radiation it emits. The effectiveness of a surface in emitting or absorbing radiation is called emissivity, which ranges from 0 to 1. A perfect blackbody has an emissivity of 1, meaning it emits and absorbs radiation as efficiently as possible. The way surfaces exchange radiation depends on their shape and position. The view factor, also called the configuration factor, measures how much radiation leaving one surface directly reaches another. If two surfaces face each other directly, the view factor is high. If they are angled or separated by obstacles, the view factor decreases. This factor is crucial because it tells us how much energy can transfer between surfaces based on their geometry. In addition to shape, surface properties matter. Surface and space resistances are concepts used to understand how easily radiation passes between surfaces. Surface resistance relates to the emissivity of the materials, while space resistance considers the distance and obstacles between the surfaces. Think of it like electrical resistances in a circuit, limiting the flow of heat instead of current. To calculate the net heat transfer through radiation between two surfaces, engineers often use an analogy to electrical circuits. The temperature difference raised to the fourth power acts like a voltage, and the combined resistances act like resistors. This helps us find the actual energy flow. In real-world applications, radiative exchange is vital. For example, in designing furnaces or heat shields, understanding how surfaces emit and absorb radiation helps optimize efficiency. In space technology, radiation is often the dominant mode of heat transfer because there is no air or fluid to conduct or convect heat. Electronic devices and engines also relying on radiative heat transfer for thermal management. Modeling this process accurately involves considering surface properties, shapes, and how shadows or obstacles affect radiation paths. Techniques like direct area integration, ray tracing, and hemicube methods are used to simulate complex systems. These calculations help engineers predict how heat moves in everything from spacecraft to industrial ovens. In summary, radiative exchange is how thermal energy moves between surfaces through electromagnetic waves, influenced by surface qualities and geometry. It's a key part of heat transfer analysis in mechanical engineering, helping us design safer, more efficient systems.